Okay, so, well, actually, thanks to the organizers for this nice invitation, and thanks to the European Research Council for funding the research that I'll try to summarize in this talk. So I decided to be lazy and use as a title just the acronym of the project. So this is a project, and what I will be talking about is the result of collaborations with a number of postdoc students and colleagues. This is only a sampler of those who did the main work that I will talk about. So the basic idea that I would like to try to promote here is that there are some fruitful connections between signal processing and machine learning, and between all the activity that has been around dimension reduction and compressive sensing that could be leveraged in maybe ways that have not been completely explored in machine learning. So the idea there is, can we develop some kind of compressive machine learning approaches that leverage ideas from dimension reduction? So as I'm stating it with a question, there will be more questions than answers, but I will provide some case studies on namely compressive clustering approaches that leverage some random Fourier sampling ideas, and on compressive Gaussian mixture model estimation. Then we'll see that, okay, there are a few things that can be leveraged, the few results about dimension reduction and information preservation, so kind of information theoretic guarantees. And okay, we'll see how far we can get there. So my one-slide view on machine learning is that we have data, and we have some task which consist in which more or less at some stage consists in inferring some parameters, the parameters of a classifier, the centroids of when you do vector quantization, but lots of data and some parameters to estimate. One of the main issues being how generalizable will be the results that you get from these learned parameters when you get new data with the same underlying distribution. So here, take your favorite example from unsupervised techniques, PCA, clustering, dictionary learning, or supervised techniques where you're considering classification. So one classical way of seeing it, but I would like to emphasize it, is to use a geometric viewpoint on this type of problem. So we consider the data as a cloud of points in high dimensions. And here, well, the cloud of points has some structure. Maybe the task is to infer this structure. But in any case, you can either represent as a point of clouds or as a collection of columns from a large matrix. And maybe it is important because in many talks that was maybe the rows of the matrix. So here I'm using columns.
Yeah, the proper way is by rows.
I know, no, but I know, but I can help. These will be columns, and this will be convenient. So. Actually, it's so much more convenient with columns.
I agree, it's more convenient, but the data come line by line. So in the text file, one data.
Yeah, that's a remark from somebody who manipulates actually data files. I don't.
Yeah, I am the one that does that.
When you store them in MATLAB, they come as columns.
Okay, go ahead. Sorry.
But anyway, okay. So data, we say high dimensional. There are two types of high dimensions: the dimension of each column, so the dimension of the features. So if each column is an image or a signal, it can be already millions of dimensions. But more reasonably, if it's a SIFT descriptor, it's already a few hundred dimensions. The other large dimension is more the volume of the collection, of the training collection. And so somehow the question I want to address is how much can we hope to compress this whole collection before we even start performing some learning tasks. So there are different ways of compressing. One way, again, let's try to use this geometric picture, is we have, let's think about each column of the matrix as a high dimensional vector. So it lives in a high dimensional vector space, but we can use some projections, some sketching, low-dimensional projection to map it to a lower-dimensional vector. So we get a collection of lower-dimensional vectors. In certain cases, maybe this is enough. But, and this is actually something that has been used already in machine learning. For example, in the work of Kalderbank, in most of the cases, this requires some knowledge, some model on the geometry of your point of clouds, your cloud of points, that it has some low-dimensional structure. Another issue is that, well, probably the impact is limited when really you have a large collections. If you have a large collection, reducing the dimension of each feature vector, well, has some impact, but quite limited. So there is an even stronger challenges in the era of large collections to compress the collection size itself. So we can think of these collections as large point clouds, but there's an alternate way of trying to reduce the size of a collection, which again is related to the talk of Garvesh this morning. There's somehow the idea of sketching or sampling. So core sets that I know very little, but I think are related to sampling methods, where you find either clever ways of sampling in your data collections points that will be relevant to your task. So this maybe through leverage scores. There's also more sketching-based approaches. I'm thinking of the early works of the Thaper, Cormode, etc., with histograms that can be histograms in low dimension that can be with a finite number of bins. You can consider them as vectors, and you can actually sketch them. However, when you're really in high dimension, you cannot afford to even build a histogram. Or you don't even know how to discretize, how you would discretize space. So this calls for other approaches. But the spirit that we'll be investigating and that we have been investigating is that of sketching, with the idea that you start from a collection and you consider actually this collection as representative as the empirical probability distribution of your data. And what you would like to build is a sketching operator that will start from the collection and build a finite dimensional vector, the sketch. This sketch will usually be nonlinear in the vectors themselves, but should be designed so as to somehow preserve the information content of your data relative to the task that you want to perform. So the sketch will be nonlinear in the feature vectors, but the idea is that we can build it to be linear in the probability distribution of the data. And that's actually quite easy. This linearity will be what what favors a number of parallels with inverse problems and sparse reconstruction. So before we go further, let's take an example. So here I'm not yet describing what's the nature of the sketch, but this is an example of compressive clustering. So here I just draw a cloud of points. So that was drawn from an artificial mixture of 4 Gaussians. I guess you see that there are 4 clusters. So they're not too separated, but they're not too mixed either. The blue centers are the actual centroids of each of the Gaussians. And here we design an algorithm that's an approach, 2-step. First step, we sketch. We compute a 60-dimensional vector. And from this vector only, so we completely forget the rest of the collection, from this vector, through an algorithm that's inspired by sparse reconstruction algorithms, we estimate the centroids of the Gaussians. And here you can see a fairly good match between the estimated centroids and the original ones.
So here you take the data matrix and you transform it to your sketch vector. One sketch vector, not per data point. That's what you're saying.
Exactly. So this is an aggregated description of the whole data matrix. Let me maybe contrast with what I understood from Garvesh's talk. In your talk, the matrix was sketched with a linear, by multiplying by a linear projection. Right. And here, what the sketch I'm going to build is not a linear projection of the data vectors. It's not a linear projection of the individual data vectors, not of the rows of the matrices there, but it's going to be linear in the probability distribution of the data. But this should be clearer in a few slides. So what are the potential impacts of these types of methods? Well, in terms of memory and computational resources, if you have an increasing collection size, typical methods for clustering like k-means or in Gaussian mixture models, expectation maximization algorithm will have a cost indicated by the pink curve that grows with the collection size. Here, with this type of approaches, you have to sketch the collection. So there's something linear in the collection size, but we'll see this can be distributed. So this is the yellow curve. It's linear in the collection size, but it's not that costly. And there's a fixed cost associated to reconstruct learning from your sketch. So if the collection size is not is relatively small, it's not really worth it. But when you get to large collection size, essentially you have a fixed cost for learning. And in terms of so both in terms of memory and well, in terms of memory, it's even clearer. You have a fixed size sketch, so somehow you're forgetting the collection, and you can do it on you can compute the sketch online, as we will see. So. Yes. But
from a statistical perspective, wouldn't you want that the size of the sketch should increase with the data?
It is possible. Yeah. So for the moment, let's say to make things simpler, let's think about you have a given task and you have a fixed size sketch. Actually, it's relatively easy. For example, with doubling schemes, to have to progressively increase the size of your sketch. But it's not clear in which scenario it is desirable, depending on the trade-off between accuracy and complexity that you may want to reach. So let's keep it simple. Let's think of it as a fixed size. And one of the questions will be, okay, what is the order of size of sketch that is reasonable? Again, I have more questions than answers regarding this. So just to make it maybe try to make it clearer what I mean by this sketch, it's the idea is to make a parallel with this geometric picture I had before. So in signal processing, we're used to thinking about the objects that we manipulate are vectors in a finite dimensional space, sampled signals, sampled images, and so we do low dimensional projections. Here in machine learning, somehow or in statistics, the natural object to manipulate is the distribution of your data. And you would like to compute something linear in the distribution of your data, but that maps it to a finite dimension, from which you gather some relevant information. How can you do it? Well, if you really had your distribution, you could simply choose a number of functions and you compute the expectations of these functions. And you see that the expectation of each function is linear in the underlying distribution. And you can also estimate it with finitely many samples by simply an average, an empirical average. But you could choose those other estimators, more robust estimators of these functions if needed. So this is both, this is nonlinear in the feature vectors because the HL functions that you choose here can be nonlinear. Probably should be nonlinear, but this is linear in the distribution. And somehow this, we've realized recently that this can be interpreted as a finite dimensional version of the min map embeddings. So you take a distribution and you map it to a Hilbert space, here a finite dimensional Hilbert space where you can measure distances and okay, work with it. Any questions at this stage? So with this idea of okay, using a sketching trick this type of sketching trick for machine learning, we can also try to mimic the questions that have been addressed in signal processing around the notion. Well, the focus was on inverse problems. Here, that would be once you've chosen a sketch, recovering a distribution from the sketch is a sort of method, generalized method of moments. But probably this, you don't necessarily want to do density estimation, So the metric with which you're interested in the reconstruction of your density is actually might be related to the task, the learning task that you have to consider. And we'll see also that, well, it's a generalized method of moments, but we want to do some dimension reduction. So in fact, we have the possibility to choose the sketch. In signal processing, this would be compressive sensing. You do, or this would be in computer science. It would be sketching. You design them to preserve information and probably to have some also computational, favorable computational aspects. Well, here we'd like to do the same thing, and compressive learning would be about designing sketches with similar properties.
So, like a naive question, can't we consider something like the empirical risk as some sort of sketch of the data? If you could somehow take the data and...
Absolutely. The empirical risk is some sort of sketch, except that in fact, usually it's an infinite dimensional sketch because you have to use the whole family of possible values of parameters. So if you only have to do, let's say, hypothesis testing, or I mean, you have to compare the risk of a finite number of parameters, sure, you get a sketch. That's a natural sketch. In fact, more generally, the question is somehow, can you design a finite dimensional sketch that gathers enough information that you can reconstruct your empirical risk? Or at least find the minimizer of your empirical risk. So before, so that was for the general picture I'm trying to explore here with you. Now I would like to give some highlights on some compressive learning examples, mostly heuristic. So they're done within the PhD thesis of Anthony Bourrier, Nicolas Keriven, who is still under his PhD, and in collaboration with Patrick Perez. So we've seen that the idea is we take a point cloud, consider it as an empirical probability distribution of your data, and we design a sketching operator. Typically, a sketch takes this form. You have to choose functions IHL, and the challenge is to choose them so that they preserve the information relevant for your problem. So let us go back to this compressive clustering example that I showed. So the standard approach here would be k-means. So with k-means, you alternate your clusters, you manipulate all your data and draw Voronoi cells, etc. Here, the way we designed the sketch was by doing some analogy with signal processing, where we know that if something is spatially localized, sampling it in the Fourier domain is a good way to make sure that we don't miss it, anything. So think of a signal that is perfectly spatially localized. If you do only a few random samples, you will probably miss the information that was present, unless you have many samples. But if you sample with Fourier in Fourier, everything is well known to work now. So we use this analogy here. Having few clusters means, I mean, the ideal approximation of clusters are Diracs. If you have k clusters, actually they are k Diracs. And here, a good way to sample such a distribution would be to sample in the Fourier domain. So sampling in the Fourier domain simply means sampling the characteristic function of your distribution. And here we are sampling the empirical characteristic function. So the sketches that we used.
So this is related to, I think, what you said about the relationship to mean mapping. So you just kind of assume that HL belongs to like a kernel or an RKHS. I mean, is this basically doing like linear sketching but on transformed features? So if you transform your X's and then do...
This is related to... there are actually, you can think of it, and we're still working on the relations, as probably a good way to design sketches is to design a kernel mean map that's a priori infinite dimensional and sample it. But the interplay between the two and the dimensions that you can use to sample is not completely clear for us at this stage. So here, precisely, well, here we're starting from the signal processing intuition that you sample in the Fourier domain. You sample the empirical characteristic function. So essentially what you have to choose is certain frequencies, omegas. And in fact, when you look at it and you think about random Fourier features, this is very related. So this is not directly a random Fourier feature, but this is a pooled, this is the empirical average of certain random Fourier features. That's a description of the distribution of your data. So this is the sketch, and well, behind there's also a lot of questions on how you should choose the sampling frequencies. These are details I will not give in this presentation. There's still a lot of, I mean, we have heuristics that needs to be related, I think, to these kernel min-map embeddings to have proper choices. So if you're interested in more details, there's a recent paper at ICASP that's presenting this week, actually, by Nicolas Keriven. Okay, so in this case, so we use this type of sketching. So with 30 complex valued numbers, so 60 entries. Sample the characteristic function, and the result, how do we obtain the result? We need an algorithm that starts from the sketch and performs the estimation of the centroids. For that, we need to exploit, we need some model. I mean, we have taken an arbitrary distribution and sketched it, so there's no way we can reconstruct it without a model, and the model here is a Gaussian mixture model with equal variance. So all variances are identity. So the only parameters are the weights of the cluster of the Gaussians or the clusters, and their centroids. So if you assume that your distribution is a mixture of Gaussians, by linearity of the sketching operator, the sketch is itself a mixture of sketch Gaussians. The good news is that when you take a Gaussian, the characteristic function has an analytic expression, so you can everything can be written explicitly, and you can design an algorithm that will perform the decoding, the reconstruction, inspired by that mimics orthogonal matching pursuits, and exploits certain gradient descents, leveraging the explicit expressions of the gradients with respect to the parameters to perform this reconstruction. So this is something, actually we leverage orthogonal matching pursuit with replacement rather than OMP, which brings significantly better results because of somehow the better ability to escape from local minima. And that's my hand-waving interpretation. We have no analysis of the convergence of or guarantees for this algorithm for the moment, but we just observe that it performs really well. Well, I'll show some more examples. So this is for compressive clustering. Now, can we extend it to more types of problems? Well, there's something. I've already used a mixture of Gaussians with equal, with identity covariances. It's not difficult to extend it to compressive Gaussian mixture models. So what we've done, we've not completely relaxed taken the arbitrary Gaussian mixture model, just with diagonal covariance matrices. That's already a richer set. And with it, you can adapt the algorithm. So either reuse the algorithm we had before, but just use gradients with respect to these non-constrained Gaussians, or, and that will be used in the next experiments, have something which gives a computationally more efficient algorithm, but not designed for clustered scenarios, more for scenarios where you have overlapping Gaussians. You don't really want to recover the centers, but you want the Gaussians to fit well. So this is using hierarchical splitting to accelerate the algorithm. Any question? So let's see an example of, well, it's a proof of concept of how this can be used in a large-scale scenario. The scenario we consider is speaker verification. So how are you familiar with speaker verification? So who is not familiar with speaker verification? Good. So In a word, speaker verification is something where well, suppose you're calling your bank and you say, I'm Rémi Gribonval and I would like to transfer all my money to the following account number. Probably, I mean, you're claiming an identity, and speaker verification is about checking that this is the identity is the one you claim. So it's not about deciding about among a million of identities who you are. It's just checking whether you are the person you claim. This is typically done with trained models of each of the possible claimed identities. But in general, you have very little data to train for a given model. So the way you train a model is in 2 steps. First, you build a so-called world model with as much data as you can, representatives of a very wide diversity of speakers. And then you'll adapt these models to be representative of each speaker. So there's a step where you take a large collection, and here we use the 2005 NIST database of 50 gigabytes of data. So, okay, for our scale, this is big. Maybe this is small compared to the petabytes that some may be manipulating. But this is, okay, thousands of hours of speech. And here you learn a Gaussian mixture model. So 2 approaches will use either expectation maximization or the proposed algorithm. Now you've learned this model, and there's a so-called adaptation procedure for each claimed identity. And now when Alice calls and asks to transfer some money, so here is the speech that is pronounced. It is compared both to the world model and to the claimed identity, and generalized likelihood test. I mean, a likelihood test is conducted to decide whether we accept the transaction or not. So what we did was to compare the compressive approach with the classical EM approach in this setting. So if you look at in more details at the database that is used to learn this universal background model, this is a database of so first 1,000 hours of speech. Now, what are the individual vectors that we consider? Well, the speech is cut into small time frames, and on each time frame, you compute MFCC coefficients in dimension 12. So you don't need to know what are MFCC coefficients. This is the equivalent of SIFT in audio. So if you take the whole database, there's the 300 million such coefficients. In fact, if you look carefully, there are many of these coefficients that corresponds to inactive no speech. I mean, there's silence between 2 words, and so there are some coefficients that are not really helpful for learning, and it's a standard technique to first do silence detection. But even after silence detection, you still have 60 million vectors in your training collection. And in fact, when we use a state-of-the-art EM C++ toolbox, the maximum size that it can manage is 300,000 samples that fit in memory. So we learned, so we first conducted an experiment with this number of training samples, either with the compressive approach or with expectation maximization. And here you can see the picture. So this is essentially a false positive versus false negative curve, where so the lower the better, and each color, so the violet curve corresponds to EM. The rest corresponds to the proposed approach with various sketch sizes. So you can see that, okay, if you increase the sketch size, it gets better, but it doesn't quite reach the quality of EM. Now remember that EM was limited by the collection size. We couldn't run it with more data. And our method can, yes?
So here was the sketch using also those random Fourier features?
Absolutely.
Okay. And what was the sampling frequency?
The sampling frequency. Okay, so the W's, I said there's a heuristic that developed in the papers, but essentially, so they're isotropically distributed And radially, there's a distribution which has low density around the origin, because all distribution, essentially the characteristic function is always 1 at the origin, and even though you have classical polynomial moments that you could measure implicitly there's not much information. And so there's a heuristic that samples more where the gradient with respect to the parameters of your model is expected to be high. So with this sampling strategy, we can run the proposed approach with the 60 million, with the sketch computed on 60 million samples. And here, what we get is that for a sufficiently large sketch size, we go below the EM curve, so the results are getting better. So in details here, we use a small sketch, so it's a 500 samples represent the 60 million collection, and from this small representation, we're not quite at the performance of EM, but not that far. If we want to match essentially the performance of EM, we simply take twice the number of the size of the sketch, and with a slightly larger size of collection. So compared to the size of the, slightly larger sketch size compared to the initial collection, you get something better than EM. So this is really a proof of concept. I'm not claiming this is comparing to state of the art. The EM is probably no longer the state of the art in speaker verification. But this is to give you an idea that, yes, there's, by simply unrolling these ideas, this parallel, you get something that's, that is not, well, that somehow exploits the fact that you have a large training collection, and that's by really capturing empirical averages over a larger collection, probably you capture more of the diversity of the collection, and so you can exploit it better than if you were simply sampling 300,000 samples from the collection. And well, this is where you could also wonder, should I increase the sketch size? Well, you see that's probably if you have a few samples, you can take a small collection, but if you have more samples, you'd like to really benefit from the more samples by starting to increase the sketch size. Okay, how much time do I have?
20 minutes.
Okay. Now, there are a few things I would like to talk about after this illustration of the general ideas of sketching. The first one is, okay, let's say it's an interlude about how this can be implemented and potential computational efficiency. And then we'll dig into some of the possible theoretical connections with what is known in inverse problems and compressive sensing. So regarding computational efficiency, well, this is the expression of the sketches as we propose to compute them, with essentially averaging random Fourier features. So in terms of architecture, you start from your large collection of training samples, and then there's your matrix of, so the rows of W here are the frequencies where you sample your empirical characteristic function. So you first enlarge, you have to measure more frequencies than the initial dimension of your vectors. So you first enlarge your vectors, apply a nonlinearity, which is the complex exponential, and then average to compute the sketch. So this is probably reminiscent of, okay, one layer of a network. And I believe there may be more connections with neural networks there, but they are still to be investigated. There's some work, some recent work by the group of Duke on some information preservation guarantees for neural networks. But I think they consider more the information preservation in the sense of being able to reconstruct the initial data. And here, the take-home message would be rather that the information that's important is the distribution of the data that you want to preserve. At least in this scenario, this is what is considered. Okay, this is the architecture. When you think about it in terms of privacy, and this is related to I think that was partly mentioned. Well, once you've computed the sketch, you just hand out the sketch, not the rest of the data. So to some extent, this could help with some privacy issues, of course. If the sketch has sufficient information to perform certain tasks, well, you will not be private with respect to these tasks. But if we can investigate further the information preservation guarantees with lower bounds and upper bounds, we may expect to have lower bounds that ensure that there's not enough information to perform certain tasks with a sketch. So besides, of course, this is you can compute the sketch itself online, so it's compatible with streaming and compatible with distributed computing. So in summary, with these sketches in this particular compressive GMM scenario, you start from a large collection and you compute a sketch. So you achieve high dimension reduction, and then you're able, with certain algorithms that are memory efficient and relatively computationally efficient, to extract your information, provided that everything has been designed and that you have guarantees of information preservation. So in this talk, I've shown empirical evidence of scenarios where you seem to have information preservation. And we'll see what could be roads towards proving information preservation. So this is related to work we did a couple of years ago with Anthony Bourrier, Mike Davis, Tomer Peleg, and Patrick Perez. So with the idea that there are techniques classically used to analyze low-rank matrix completion, sparse recovery, general inverse problems in general that actually have some really large generality, and that maybe they're worth packaging in a sufficiently universal way. So typically, in inverse problems, you consider that you have a high-dimensional vector, you observe a low-dimensional version. So without further information, there's no way you can hope to reconstruct. But if you know that your data comes from is well approximated by a sparse vector, then there are algorithms with reconstruction guarantees. So under certain now well-known conditions for k-sparse recovery, you're able to build an algorithm that we will call a decoder here. This is the terminology introduced in a nice paper by Albert Cohen, Ron DeVore, and Wolfgang Dahmen. So these decoders, ideally from your measurements, you want to be able to build a decoder that has some reconstruction guarantees. Here the reconstruction is that with metric that I will leave quite fuzzy. So the decoder delta, even if you have some noise on your data, the reconstruction of your X will be controlled essentially by the size of the noise if your data satisfied your model. So if it is exactly k-sparse here. So this has been investigated. I mean, we know there are cases where there are such decoders, but the nice work of Cohen and co-authors was to investigate the fundamental information theoretic question is, okay, when are there, can I expect such a decoder to exist? So we know a number of decoders, L1 minimization, greedy algorithms, and so on. I expect that a number of you are more or less familiar with this. And in terms of guarantees, one possible focus is so-called uniform guarantees, worst-case guarantees. They're related to the well-known restricted isometry property. So now a question, who is not familiar with the restricted isometry property? Okay, enough people that I will spend some time explaining. So these algorithms, they are designed to recover k-sparse vectors. So you have k-sparse vectors, you project them to low dimension, and what you would like to be sure is that there's no way you can confuse two k-sparse vectors. So if you have one k-sparse vector and another, and that you project them and get essentially the same representation, then you're lost. There's no way you can hope to reconstruct k-sparse vectors. The restricted isometry property is essentially something that just says that if you take two k-sparse vectors that are sufficiently distant in the original space, they will remain distant in the in your observation space. And this means that considering the difference between two k-sparse vectors, it's a vector that has 2k non-zero components. This is the expression of the restricted isometry property. It preserves the norm for every 2 k-sparse vector. So this is what is known for in the case of sparse recovery, but actually there's a number of other models that have been considered in the literature. So related work has been done with low rank, with sparse vectors, with vectors that are sparse in a dictionary, and a number of other low dimension models. Pick your favorite one. So in our case, we would be in particular interested with models where the low dimensionality comes from the fact that you have a mixture of few Gaussians, so you have few parameters somehow. And you would be like to consider something that doesn't really live in a finite dimensional vector space, but in the space of probability distributions or finite sign measures. So the question is still the same. Okay, if you're given some model, some low dimensional model, and for the moment let's not specify what we mean by a low dimensional model in some space, and you have some measurement operator, think of the sketching operator. When can we expect that there exists some reconstruction algorithm? So that there exists a decoder with instance optimality guarantees. This is a question that is not new, that has been, that is related to all questions from the 40s in the literature on embeddings, where people have been investigating questions such as, I have this fractal set here, and can I map it to finite dimension, and what is the dimension I can map it to? But I will not develop this further. Here, we'll see that actually the existence of such decoders is again related to a generalized notion of restricted isometry property. So instead of stating one new restricted isometry property for each type of model, why not state one for any model set? And here it is. So we consider sigma, which is some subset of your ambient space. And you'll say that your measurement operator M satisfies a restricted isometry property on this model, or actually on the secant set of this model, that it's the difference vectors between two vectors of the model. If, this inequality holds. So here I wrote it in an asymmetric way, but you can write it with the usual way, with 1 minus delta, 1 plus delta in a straightforward manner. And it's possible to show that, in fact, if there exists a decoder with this reconstruction guarantees, then necessarily the matrix M that you're considering satisfies the restricted isometry property. This is just an analysis of the worst case conditions. And the second result, which is probably the most interesting, is that, in fact, if the restricted isometry property holds, then there is indeed a decoder with reconstruction guarantees. I come back to the decoder. You're anticipating on my next 40 slides.
40?
Just kidding. So it's just an existence result. So this is why I say it's information theoretic results rather than, it's not dealing with the complexity trade-offs. There are many nice questions around it. I'll try to evoke some of them. So here it implies, so if your matrix, your measurement operator, because you're not necessarily in finite dimension, it's not necessarily a matrix, satisfies a RIP, then there is a decoder that provides exact recovery with stability to noise. So whenever you take X, which is in your model set, sigma. You measure it, you add some noise. The decoder provides an error proportional to the noise, the size of the noise. So this is just an extension. I mean, the proof just follows from rewriting that in the work of Cohen, but we've just shown that it can be extended to an arbitrary model set. And something, a bonus is that that's probably the main difference with the early embedding results from the results from the literature on embedding is that there is also some stability to modeling error. So even if your initial signal does not exactly belong to your model set, but if it is close enough with the metric that's also related to your model sets, then I mean, you measure its distance. It doesn't need to be close enough. You measure its distance, and then there's an additive term in your inequality. So this is both stable to noise and robust to modeling error. Now, of course, Francis asked, yes, but what's the decoder? So some work done this year with Yann Traemblin will try to provide some answers. But first, maybe I need to just exhibit what's the decoder in the proof, in the previous proof. So you know that you have a matrix with the restricted isometry. There's a decoder. What's the decoder? Well, it's written here. So given your observation, well, you find the x that minimizes the weighted sum of your data fidelity plus your distance to the model set. You're happy to, how do you manipulate this? In particular, if your distance is not so.
You can do MCMC.
Well, so in certain cases, so here the distance d sigma may look abstract. In certain cases, it's essentially the L1 norm. So it could look okay, except that you're computing the distance to k-sparse vectors. So that's not nice to manipulate. So the good news is that this decoder is also noise blind. You don't need to know the noise level. This decoder will work and provide these guarantees, whatever the noise level. So you don't need to tune the noise level to begin with. But I agree, it's not very convenient. Something slightly more convenient is was proposed by Thomas Blumensath, who proposed with Mike Davis the iterative half thresholding algorithm for sparse reconstruction. And the projected Landweber algorithm is just a generalization to an arbitrary set. So here's something connected to the talk of Alexandre Daspremont yesterday, who manipulated prox, and there was a question by Guillaume Obozinski on, yes, but what if the prox is not so easily computable? This will pop up here. So the idea of the projected Landweber algorithm is simply that it's an iterative, I mean, it's a projected gradient, right? You do at each step some gradient to decrease the data fidelity term, that's when it's an L2 term, and then you project to the closest point on your model set. So that's perfectly fine when you have your model set is k-sparse vectors or lower rank matrices, vector sets for which you know how to do it efficiently. But it's easy to exhibit a number of cases where it's NP hard to compute these procs. Okay, so this opens a number of questions on maybe characterizing what are the model sets for which you have actually something a prox that is computable, because for these you may have dimension reduction and computability, which would be nice. And in this case, there's a proof of convergence. So with a well-chosen step size related to the constants in the restricted isometry property of your matrix, corresponding to delta smaller than 1/5, you can prove that this algorithm is convergent and that it recovers stably no, you can prove that the iterates provide a stable recovery. So if your data was in your model set, you recover it exactly. I mean, you converge to it. And if you're not in your model set, you may not be convergent, but you will circle within a ball that's not too far from the noise level and the modeling error. Again, okay, maybe not so convenient, and since there were a number of talks on convex optimization, maybe what you would rather be expecting is something of this type, where the decoders that are based on the minimization of some functional. So we know a number of them. So the decoder would be, I try to find among all solutions within the prescribed data fidelity, the one that minimizes some regularizer f of x. So if you take sparse vectors, f, L1 norm, etc., etc. Well, for a number of such model pairs of model sets and regularizer, many authors have proved that if the restricted isometry property is below a certain constant, then this is an instance optimal decoder. So in particular, the results of Kai and Zhang are known to be sharp. So the 1/√2 cannot be improved for L1 minimization. Closing an endless story of work showing that the 0.41, 0.42, 43.5 were working. But still, every time you get a new model and try a new regularizer, there's a new guarantee to be obtained. Well, that's what we investigated with Xiao Tranmien was the existence of an underlying principle. And we got one. So please don't read this small fonts. It's small fonts just to be so that you don't read it. So in fact, if you have a model set that's simply a homogeneous set, so it's a cone. If you multiply by a positive scalar, you remain in your model set. Or that includes the case of unions of subspaces that are stable by simpler linear multiplication. And you take any regularizer, you can actually define a restricted isometry property constant. So it just depends on your model set and your regularizer. And with this, you can say that any measurement matrix that has a RIP with delta smaller than this particular constant will be compatible with regularization with F on your model, and the corresponding decoding will work. Will have guarantees. So what we would have liked to do would be take a model set, find out automatically what's the right regularizer.
As the atomic norm.
So at first we thought that atomic norms would do it. The paper on atomic norms is nice, but if you look carefully at it, what it does is say, okay, here is my model set. But in fact, this model set has special points in it. And these I call the atoms. And they have, in fact, special properties that I don't really discuss on certain orthogonality properties between atoms. And from this, I build an atomic norm that will work.
I mean, like, does the atoms to be at the extreme points of the atomic norm, no?
Yeah, but there's there's an example. If you simply take your model set to be the set of two sparse vectors. So probably the natural way of designing atoms would be I take every normalized two sparse vector, and then the atomic norm is the so-called K support norm with K equals 2. And it doesn't allow recovery of points that are at the corners of the L1 ball because the atomic norm is flat. So it's a bit. I think the question of starting from the model and constructing the regularizer is still an interesting and open one.
So, okay, to your extent, if you start from a norm, you can define a model class that will be adapted to a norm with constants.
That way you can do it. I mean, starting from a norm, yeah, but I'm interested in the reverse way. Starting from a model, which are the vectors you want to reconstruct, how do you build your regularizer? And one possible way that we'd like to investigate is to try to design it so as to maximize this constant.
But you may also have, like, we have done some work with Guillaume Boutinsky showing that some sets do not have good convex relaxations. So it may be possible that it is impossible to design. Assuming F is convex and compatible, may squash many types of model classes into like simpler ones. So it may be impossible.
Yes, it may be impossible to have a convex one. Here I didn't even say that it's f is convex. Take some f, some sigma, I can define this, but
Applied it more.
okay, then at some point you need to optimize, to be able to optimize with it. But sometimes f is not convex, but if you look at the squared loss plus f, it's convex. So in certain cases, there's work by Ivan Selesnik on that. Sometimes it's the overall problem that you pose is convex, even though the penalty is not. Okay, so just to give you an example of what can be obtained with the results, and I probably at -1. I mean, now you can you can unroll the mechanics of the previous theorem and recover existing results, get sharp results for new examples. For example, I don't know if anybody is interested in recovering permutation matrices from low-dimensional projections, but you can do it provided you have RIP 2/3, and that can be achieved with, I mean, you can design dimension reduction operators that satisfy this RIP with a number of measurements that's controlled. I don't have in mind the covering numbers of the set of permutation matrices, but that can be done. So since I'm a bit short, I probably skip this. That was just to illustrate the idea that you can already use this technique to somehow design a regularizer for a model. So for certain model, you could either use the L1 norm that is done in classical papers, or knowing the sparsity in different blocks, weight the L1 norm, and with this weighted L1 norm, you have RIP constants that are higher, so better recovery guarantees. So, highly time to conclude. The main message I try to convey here is that there are interesting parallels to be done between signal processing, machine learning, and with the idea that compressive sensing could maybe give rise to the compressive learning techniques with the ability to reduce, substantially reduce the size of the collection while preserving the information necessary to perform the task that you want. And I illustrated it with particular sketches that are nonlinear in the data, but linear in the probability distribution. Now, just the last minutes for some advertisement for some further results that I couldn't fit in the previous hour. So for the compressive clustering and compressive GMM, these are the references of the papers where they can be found. Now, regarding information preservation, what I showed with this restricted isometry property is the first layer of the story for a worst case analysis, guaranteeing that the information is there in your low dimensional projection. The story is here. Now there's the question of how much dimension reduction can you perform while actually preserving. Well, this is. There are many works currently trying to generalize, well, essentially Johnson-Dinderstrauss lemma to general model sets. In particular, there's the work of Dirksen that establishes that the links between the Gaussian width as a measure of dimension and how much you can reduce, you can hope to. What's the dimension you can hope to project to. But it seems that it is not yet the end of the story and that this dimension is not sharp. So there are questions about what is the right measure of dimension for a model set. And in particular, when you have a given learning task, how should you measure it? So some of the questions around this are related to somehow the notion of compressive statistical learning. So what you want to reconstruct is the risk functional. For certain risk functional, we now know that you can actually characterize the intrinsic dimension of sketching that is needed to achieve it. But many questions remain open. So thank you for your patience and attention.
Are there some questions or comments?
you use the RIP property to do the analysis, but is it easy to be satisfied? Because I read the paper of one paper of Candace. It studies the matrix completion problem. It says that it is not likely that the RIP will be satisfied for the matrix completion problem.
Absolutely. For the matrix, the RIP, the restricted isometric property, is necessary and sufficient to have uniform worst-case reconstruction guarantees. But there are many analyses that do not require worst-case analysis, and that as somehow related to Quentin's talk, there's a typical behavior. In particular, in the matrix. So if you do low-rank matrix reconstruction, there are ways of sampling low-rank matrices which satisfy the restricted isometric property. But this is not the pointwise sampling corresponding to matrix completion. So if you want to do matrix completion where you have sampled a matrix at few points, the measurement operator will never satisfy the restricted isometric property, because you can find very simple low-rank matrices that will just fit one at a non-observed location. So the restricted isometric property is feasible, but with measurements that measure essentially all coefficients at once. Does it answer your question?
So you mean that although it does not apply to the matrix completion problem, maybe it can be applied to the matrix approximation problem?
It applies to matrix reconstruction problems with certain types of observations, but not with observations that are related to the Netflix problem or so, where you have unobserved entries and observed entries.
For key-sparse vectors, it's hard to check that a given linear application M will satisfy this property. Are there particular cases that you studied where it can be very easy to check?
There's one, but I'm not sure you will be interested in it. If your model set is a linear subspace, then it's a condition number that you essentially. But the observation will still turn out to be useful in certain scenarios where actually you just revisit it under the same umbrella. But
apart from that,
apart from that, I think this is typically difficult. I mean, there are papers now showing NP hardness of certain specified problems related to the computing, testing whether the restricted isometric property, the restricted isometric constant exceeds a certain threshold.
Other questions?
Could you say something about Chepakov's RE property? Could it also be used to simplify this analysis, or will it help in this case?
So you're talking about the restricted eigenvalue property?
Yeah.
Okay. There I'm in a slightly less familiar context, but as far as I know, it's related to the descent cones of a particular cost function. So here I was talking about the ability in general to do reconstruction. Is there information in your measurements or not? The restricted eigenvalue property, I think, is more related to the choice of a particular regularizer, and now you're looking at the behavior of the restricted isometry property on vectors that decrease this cost function. So this is this, I think, typically leads to non-uniform results on the non-uniform guarantees. When you have a given point, you can see how you can decrease the cost function, in which direction you can decrease the cost function, and analyze the restricted eigenvalue property there.
I have one question. From the practical point of view, how would you choose the size of the sketch? Which kind of principle can you say something for choosing the size?
Okay, so first, in the things that I didn't really take the time to evoke, there are some general arguments from when you try to generalize Johnson-Lindenström's lemma. There's the notion of there are measures of dimension of your set that naturally appear, and if the size of your sketch sufficiently exceeds this measure of dimension, you should satisfy the restricted isometry property. In particular, when you have k-sparse vectors, the k log n over k appears naturally. So, of course, there's what's the constant that needs to be tuned. But for Gaussian mixture models that we played with, you can essentially count the number of parameters. So if you have k Gaussians in dimension d, essentially, well, you have k weights or k minus 1 weights and k centroids, k variances. Do the calculus, and you know what's the size. We have empirically observed that we get phase transitions with for the algorithms with this size of sketches.
And if you only have data, say you split the data with the first part, you try to learn the minimal size of the sketch, and with the rest of the data you will.
Okay, that's a different problem I haven't paid too much attention to, which is, okay, what's the model? I mean, how to choose your model for your data. Here the point of view was rather, okay, I'm given a model, or I choose my model, and this is, I decided I will fit 64 Gaussians. How many, what's the size of the sketch I should use? The one you are evoking is, to me, seems much harder.
Okay. Well, it's time again.